I want to join in thanking actually both Barbara and Claude for organizing this workshop. I have found it, extremely useful, and I've learned a lot from just listening to all the talks yesterday and today. And thank Nicola for actually a wonderful introduction. Nicola started by saying that plate tectonics is the surface expression of mantle convection. David Berkovich is fond of saying actually that plate tectonics is mantle convection, and you really cannot decouple the two. And I just want to go a little bit further today on that concept by actually looking at topography and the surface deformation that implies and how that is connected to mantle flow. So if we look at the picture, the map before of topography, you see a great deal of difference between oceans and continents, a lot of deformation on the continents, and you ask yourself, what are the individual contributions to topography? When they were talking about rifting, the Ritzke showed, and Marta, they mentioned topography and the possible subsidence you get, and the issues that are related to really the crustal and density structure. So if we look at what contributes to topography, what controls the amount of topography that you have, it really, at certain wavelengths, is going to be the isostatic balance of the crust and the mantle lithosphere, inhomogeneities that you may have in the density. You will have uncompensated topography at shorter wavelengths, which is due to mountain building. And then you'll have very long wavelengths. Went the wrong way. Very long wavelength topography that is related to the vertical motions of continents and oceans, which can be due to long wavelength postglacial rebound, and especially to mantle flow. And this is what I'm going to concentrate on today. And the mantle flow here exerts radial stresses and across a density interface that will induce a deflection which is proportional to the buoyancy, essentially, to the magnitude of that radial stress, and inversely proportional to the density contrast at that interface, say crust and air, crust and water, and so on. Because these are radial stresses, these are really related to how the flow is working inside the mantle, and whether that buoyancy is under the lithosphere or at the core mantle boundary, you can still, assuming that you have a transport of mass across the upper and lower mantle, you can still induce topography even if your buoyancy is deep in the mantle. And I want to get that point across. The other thing is that, we've known for a very long time, of course, that dynamic topography is important at long wavelengths because that deflection that the dynamic topography has causes a redistribution of mass. So that where you had water, now you have rock, for example, if you have a mass anomaly that induces an upwelling here, and that redistribution of mass means that it's affecting the shape of the Earth or the gravitational potential, and this is the observed geoid right here. This has, of course, been known for a long time, and the work of Yannick Ricard and Mark Richards elucidated this in the late 80s. So dynamic topography is inevitable. And it's an important component of the gravitational shape of the Earth. Now, the problem is that to match this amount of dynamic topography, to match the geoid like this, you need a dynamic topography, if there have been some models around, that it's a peak-to-peak amplitude of about 3 kilometers. And it's hard to believe that there's actually that much topography that is purely dynamic at long wavelengths, or in fact, at short wavelengths, which we will see as well. Okay, I want to just extend a little bit on the importance of dynamic topography and the concept that is also related to surface deformation. And going on what I said before, that the dynamic topography is caused by the radial stresses that cause a real physical deflection of the surface, that implies that you're going to impose stresses on the lithosphere that are related to that mantle flow, and also that you're going to cause effective deformation of the surface. You can generate basins by tilting a continent over a subduction zone, and so on. So that means that we will see the effect of the mantle flow directly, not only on the general topography, but also on the deformation. And what sort of information do we have? I'm sorry that these are not as resolved as I hoped. What sort of information do we have about that deformation in terms of coherent patterns of what causes that deformation at the surface? So one way to look at it would be to look at the world stress map, which is a compilation. This is the release of 2008 It's a compilation of all the state of stress that we have at the surface today. What you will see here is actually the orientation of the most compressive stress in the horizontal direction, so in the plane. So the vertical stresses are like this, the maximum vertical stress, and for us that would be the biggest, but we ignore that. We just look at the planar one, and the colors will correspond to the regime. So if you want, red is extensional, normal faulting, green is strike slip, and the blue is compressional. So what do we see when we look at this compilation? We see that in fact there is a great deal of variation at short wavelengths, no doubt about it, that there is a control undoubtedly on topography, for example, and we will look at that. But we also see large regional patterns that perhaps we could relate to what's underneath. So for example, I know this isn't quite so visible here, but if you looked at the compressional stresses at the blues here, they actually form a ring that changes in orientation right in this area where we have had very long-lived subduction. And this is something that I talked about many years ago now in a paper in 2004, that in fact there are elements of very regional controlled stresses and deformation at the surface. So if we just look into a little bit more detail in terms of what the sources of stress are, I just mentioned them, of course. Some are going to come from the mantle flow, shear tractions at the base, and vertical tractions, if you wish, radial stresses. We're also going to have inhomogeneity and topography in the lithosphere, and what are right here called edge tractions. But remember that actually, if we knew the density distribution in the crust and lithosphere exactly, and in the mantle exactly, and if we knew the rheology exactly, really the only force that's acting on everything is gravity. But when we talk about edge tractions or other particular forces, you know, a ridge push or whatever the things they might be, they're really parametrizations of the fact that we don't know the buoyancy exactly, and most of all, a parametrization of our ignorance of plate boundary rheology and rheology in general. So every time people talk about slab pull, ridge push, these are all sort of proxies sometimes, in the case of slab pull, for the strength of the slab in the context of the mantle flow model. So I want to, sort of extend a little bit on this and look at some of the, some of these inhomogeneities, what they cause, and focus on Africa, and also look at the mantle flow. Nicola showed that in fact, we have to compute the mantle flow to get plate tectonics, and I just want to mention what the governing equations for that may be to reinforce a point that he made with much more flair, which was the egg with the all broken egg. So the governing equations we know, the Stokes equations, we have conservation of momentum, energy, and mass. I just want to draw your attention to the fact that if this was, we were doing things completely, we actually have to take into account the fact that that's wrong, that, viscosity is a tensor, and that there are a lot of variations spatially, for example. Okay, now there are some simplifications we can make, and those simplifications come from the fact that the mantle is very viscous, and therefore the inertial forces are not important. Therefore, all the temperature, all the time evolution comes from making the velocity a slave to the temperature field. Okay? And if we assume further that it's incompressible, possibly not, of course, because of phase transition, we can also sort of have a very simple expression for the body forces that drive the system that are related to the thermal expansion and the delta T that drives. Now, we can make the difficulty still remains that to make plates, sorry, I went the wrong way again, that to make plates, actually, we need to know this incredibly hard constitutive relationship between stresses and strain. Or another way to put it, again, not with as much flair as Nicola, is that we have faults, and it's a large range of time and length scales to try to model in a fluid, right? Where in a fluid, if you have any piecewise continuity of velocity, you're creating a singularity at those boundaries. However, instead of taking the approach of trying to put in a lot of rheological laws from the lab, which are not measured at the right strain rates, or to try to make any more proxies, you can take one further approach to the mantle flow, which is, rather than trying to predict plate tectonics ab initio, as he's doing, is to say, we know a lot about what the density distribution is, because we have wonderful models of the three-dimensional velocity structure. If we convert them to density, then we have density heterogeneity in 3 dimensions. In that case, we don't even have to solve the energy equation. At least for one time step, we can get the instantaneous flow that is related to that density heterogeneity. Simplifications, yes, and also simplifications of the rheology. So if you wish, apparently geodynamicists are fond of food images, we have to model everything from this to that, right, which is a function of the volatile content of the pressure, temperature, and stress, and that's difficult. Instead, we take a more simpler approach. So the first simplification I'm going to make is one to compute instantaneous flow from a density heterogeneity model that is assumed, in this particular case, using sitcom. And for the viscosity, the simplification we're going to make is that we're going to get lateral viscosity variations as a function of temperature, the temperature dependence of the viscosity, and the temperature dependence of the viscosity is going to come from actually taking tomographic models, converting them to temperature, and then giving you the lateral viscosity variation. Okay? Now, so we're going to compute the mantle flow like this. We're going to introduce furthermore the thickness of the lithosphere, at least as imaged from seismology. This, I actually think this is from I think this might be from Gung and Romanowicz, I don't remember. So we have some proxies for the strength of the continent, for the lateral variations in the lithosphere from having a low viscosity asthenosphere, and sort of trying to use the simplifications to get some predictions at the surface. Now, these predictions, how do they relate to the stresses? If I'm going to compute the flow and I get the shear tractions at the base, those shear tractions better match plate motions today, because those are the tractions that are going to give rise to the plate motions today. And indeed they do, without going into detail. This is Nouvelle 1A. This is the observations of plate velocities. And these are color-coded. This is the work of a former postdoc, Van Summeren, Joost Van Summeren. And you see that these are color-coded by the plate velocity magnitude. So, you know, there are things that are going very fast and things that are going very slow. And this is the average velocity, and this is the ratio of subducting to non-subducting plates. Now, if we have shallow continental roots and a global asthenosphere, so introducing some viscosity heterogeneity, those shear tractions, which should give rise to some deformation at the surface, actually match the plate motion system pretty well. The innovation here is, besides the viscosity heterogeneity, that much like that picture of the Mike Gurnes work that Nicholas showed, these are plate velocities in which the shear tractions at the bottom and the plate motions predicted match each other. Often when this work is done, often to do things like matching anisotropic fields, you get buoyancy and predict shear tractions and then impose the plate velocities that are observed. These are predicted velocities, therefore matching. There's no mismatch between the shear tractions at the base. Okay, so we have then a good handle on what those basal tractions may be, but the lithosphere, you know, in this case, in these models, this is a purely viscous system, and the lithosphere isn't deforming probably only as a viscous system. Now, as we saw in the earlier talks, we have a great deal of variability vertically in the rheology of the crust and the mantle lithosphere, but if we want to compare to, say, the world stress map and sort of measurements that is based on, we decided instead to do something simpler in terms of the rheology, that perhaps more applicable to the prediction of those stresses, and that is to construct a spherical finite element shell that it's elastic in nature, and where we could apply the shear tractions at the base, and then we could also look at the deformation due to dynamic topography. We also have weak plate boundaries, but I can talk about that later. So what do the results look like? If you just look at the horizontal shear tractions, yes, this is what you see. This is actually the outline of Africa right here, and these are the same colors as in the world stress map, color-coded by regime. And you can see that first, these are very large. in fact, you get something close to 100 megapascals. That's point number one. And point number two, that this is largely strike slip, right? So the shear tractions that are predicting plate velocities are actually giving a strike slip regime in Africa. And you have these compression that is actually due to the small, actually bending moments that we are computing in the lithosphere as well. So compression in that lithosphere. Now, is this what you expect? Well, actually, keep going the wrong way. Actually, yes, it is what you expect. If you look at the system in a much simpler way, these are the stress resultants in a membrane state of stress for an elastic medium. If you actually just focused on the last part, the stress resultant for theta, theta, and phi, phi, or the two horizontal directions, are equal and opposite to each other when there are no radial stresses. Yes? So you expect the strike slip regime is all you have the shear tractions at the base. That's exactly what you expect. In fact, the deviations are what's unexpected, and that's what comes from, the bending moments and the slight deformation that we have in that shell. Okay, so then what is, obviously then you will say there's no way that this is predicting the world stress map. Well, if you actually now add the effect of radial tractions, dynamic topography, and you look again at Africa, this is only the effect of radial tractions. Now, not unexpectedly, because we're predicting a big upwelling and mantle flow there, you actually start predicting extension. Okay? If you combine the two together, if you combine the radial tractions with the horizontal tractions, you will see that, in fact, it is the dynamic topography, it is those radial tractions that dominate the regime determination. Okay, even though the magnitudes are actually slightly bigger as well. Now, you will note, however, that this is probably not the right direction for extension for the East African Rift. And I think, although there are variations in here, but you can see by just comparison with this regional view of the world stress map that we're not predicting exactly the right direction. So that is perhaps because there isn't obviously just that mechanism. There's also the inhomogeneity of the topography, and Africa is a good place where you can see, given the large amount of topography that you have in Africa, what the effects are of both that topography and the structure of the lithosphere. So going back to something that Mike Kendall showed, I think it was mentioned by Ritzke in terms of Southern Africa. What is the topography in Africa supported by? I mean, obviously, there's going to be some topography that is purely related to that crustal architecture. And Mike showed a picture from my paper from a long time ago, which was that if you looked at just Southern Africa, where because of the crustal structure, because of the fact that it's a craton, because of the heat flow, we don't expect shallow sources to give rise to the enormous amount of residual topography, about 1,500 meters, maybe 1,000 meters that you see there, that it is due to dynamic uplift due to a mantle upwelling. Okay, so this is a newer prediction based on the S-wave tomographic model S40RTS, Jeroen Ritsema's latest incarnation, in a very simple way, converting the velocity to density and assuming that that is thermal, purely thermal. And that there's no chemical component until we've heard that part of that low velocity province could be chemical in origin. Over here is actually a residual topography to be compared to this, and you would say that agrees pretty well. This residual topography is an observed dynamic topography where you subtract the isostatic contribution from the total topography. So you will say, okay, that big upwelling is actually supporting Africa, so that dynamic topography does contribute some to that surface deformation. And maybe if you couple that with the actual crustal structure, you will get the right orientation. However, I just want to get it out there because that, in fact, this isn't the only prediction for the topography. And Ritzke said, and it's true, that it remains controversial because this is the predicted dynamic topography and the residual topography from the work of Alex Forte and Rob Mucha, and they, in fact, see subsidence. They would predict that, in fact, mantle flow would lead the continent to be pulled down in southern Africa, and this is their residual topography that matches their predicted topography. So what's going on? Okay, so you could say I'm wrong, there's chemistry, and so on. Possibly true, maybe even likely true. Although I have a hard time believing that the crustal structure of southern Africa, without this drawdown, would give you an elevation of 3,000 or 4,000 meters. Okay, so what are the differences? The differences between, here's how Alex does the mantle flow have to do with taking into account chemistry and some of the conversions of velocity to density, but there are differences more importantly in how you predict that residual topography. Here, and I'll show in a minute, I've taken into account the crustal structure, but also the mantle lithospheric structure. In this prediction, he's assumed that all isostatic contributions come purely from the crust, and that basically the entire mantle lithosphere is mobile and not contributing to the isostatic effect here. Okay, so that points out that before we can actually look at how good the dynamic topography is at that surface deformation, or even how important those topographic contributions are to the stresses, we actually need to understand the lithospheric structure, something that has been talked about greatly yesterday and today. Now, I'm going to take an abstracted view, which is a global view. Irina Artemieva has done this as well, and she was yesterday in the audience, where we say, let's make a global model with at least a few tidbits of knowledge from petrology in a very simple way. So starting from crust 2.0, divide the world into tectonic regions, don't be thrown by this calling convergence is only because the Appalachians are there. It's just trying to divide the world into simple provinces because each of those regions will have a different geotherm. And because they will have a different geotherm, they will have different properties for that mantle lithosphere as a function of pressure and temperature. So besides dividing the globe into 4 regions plus the oceans as a function of 8, you start from crust 2.0, including the lower crustal structure that crust 2.0 has, which is not necessarily good everywhere, which is generally mafic, right? And then the idea coming from all the things we've heard and is that every time you extract something that is mafic, basaltic, or you make a mid-ocean ridge basalt, there is going to be, out of the peridotite that you melt, you're going to leave behind a residuum which is depleted and which is less dense, which is Harzburgite. Okay? So in every model, we'll include not just the crustal structure directly from crust 2.0, but a lithospheric mantle that is depleted, which thickness depends on the thickness of the lower crustal layer, and an undepleted layer, so a source of more, if you wish, and that thickness then will be determined thermally. So there'll be a chemical and a thermal layer, just like in Barbara's model, or Yuan and Romanowicz. Okay, and this is the result. This is the global lithospheric model that you see, where you don't actually have such thick cratons. And this is what gives rise to that residual topography that I showed before for Africa, right here. And this is compared to 4 other models. This is now expanded to spherical harmonic degree 20. These are actually expanded, I think, to spherical harmonic degree 12. And you see, actually, there are similarities and differences. And these have different assumptions. This, in particular, just subtracts an average height for the continent, so 529 meters. Okay, so I guess the point is that the structure of the lithosphere becomes all important in determining how much dynamic topography you have, and how you determine that that structure of that lithosphere, the importance of that depleted layer is going to control how much residual topography and therefore how much dynamic topography you should expect in the surface deformation. Now, turning to the fact that we have this architecture in the lithosphere, which has actually a continent, an upper and lower crust, a depleted mantle, also a non-depleted mantle. This is going to give rise to different stresses, right? So a column of crust, so a vertical integration of the variations in density in a continent, right, will integrate to a lithostatic stress, right, so a vertical stress, the gravitational potential energy as it's called, and the variations in space of that gravitational potential energy are going to be balanced by the gradients in deviatoric stress, right? So what that means is that if you have topography but also variations in density in the lithospheric structure, you're going to get stresses, right? And that's obvious from the world stress map correlations. Now the question here is, depending on what you assume for the that structure of the lithosphere, do you get different results? Or is this really well resolved? And going back to Mike Kendall's talk on rifting for Africa, he showed the gravitational potential energy and the values that Stamps has for her calculations, which are different than mine. And they're different than mine because her assumptions of the continental lithospheric structure are different than mine. So at the top here, what you see is a map where now the white bars are extension and the black bars are compression. The colors are basically that lithostatic stress values. And although it isn't entirely obvious, these are actually two different models of continental lithosphere. It isn't completely obvious everywhere, but these are different. And there are other assumptions that make it even more different. In this particular case, everything is to 100 kilometers base depth, so 100 kilometers thick maximum lithosphere. In this case, you enforce isostasy. You allow for absolutely no dynamic topography. Because you see, the surface of the Earth contains, that topography contains dynamic topography. And therefore, if you use that topography to calculate your gravitational potential energy, you're mixing the mantle contribution and the lithospheric contribution unless you somehow remove it. So in this particular case, it is not removed. In fact, all the excess topography is enforced to go isostatic by increasing the density of the mantle. At the bottom here, instead, I'm using my lithospheric structure model where the dynamic topography has not been removed, that it's assumed to exist. If we go in more detail now to Africa again, which is a good place to go, you'll see that the overall directions, which are controlled largely by topography, are the same, but the magnitudes are slightly different. And I'm almost done here. I just want to say that, however, looking at the amplitudes of the horizontal part, which I showed you before, compared to the radial, are much larger. Okay. So that means that somehow, if you want one to be dominant over the other, you have to decouple through the lateral variations to the viscosity heterogeneity. And this is what's meant to show that. And a prize for anyone who can tell the difference between these two. One has lateral viscosity variations, the other doesn't, right? And so, in fact, this one, I think, doesn't. And there are basically no differences, right? And it's that the lateral viscosity variations, while this is not surprising, while they have increase the ratio of the traction magnitudes at the base in areas where the tractions are very large, which is shown here in the colors. These are actually basically averaged out by the transmission of stresses effectively in that elastic lithosphere, so you have very little change in the ratio of the elastic stresses. Now, this is for the horizontal part, but this is also true in the vertical part, and this is my last slide. And this is my last pointer, the take-home message, that in fact, radially changing the viscosity of that asthenosphere, making it a lot weaker, so from 10 times to 10,000 times, 4 order of magnitudes, actually has very little effect on the transmission of that stress, right? And this is illustrated here by the fact that the change in stress magnitude in terms of the proportion of the model that it covers actually doesn't change barely at all until you get to 4 orders of magnitude weaker asthenosphere. So the conclusion from that is that the mantle flow, or basically the mantle and lithosphere, are inevitably coupled. The coupling might be variable, but they're all coupled inevitably through dynamic topography, and it's very difficult to get rid of even with a very weak asthenosphere. Thank you.